a survey. Is this readable from the back? Okay, so Reven has written a very comprehensive survey on the subject of fibering rigidity. This was state of the art about 2011. So in this survey, he talks more about higher dimensional manifolds, so 4, 5, etc. But he's more interested in group theoretical obstructions to fibering. My talk today will be focused on 3 manifolds. And on, well, specifically, later I'll talk about 3 manifolds with very interesting homological structure. So to start off with, when does a 3 manifold fiber over the circle? There's a result due to stallings. Well, a condition due to stallings. A compact, irreducible, manifold M, fibers over the circle if and only if the fundamental group admits a surjection onto Z with finitely generated kernel. Okay, so we have this condition. And I'd like to say that 3 manifolds that fiber over the circle are very plentiful. So there is a theorem called the virtually fibered theorem. Due to Agol, Wise, and the work of a number of people, that says every hyperbolic 3 manifold with infinite fundamental group has a finite sheeted cover that fibers over S1. So, okay, we know that a lot of 3 manifolds do fiber. So Thurston asked himself, well, okay, if you have a 3 manifold that fibers, in how many different ways does it fiber? And so this question was completely answered by Thurston norm theory. And I'm told that I should give a very brief definition of Thurston norm theory. Okay, so Thurston defined
also follow the stage.
Is this writing big enough to read at the back? So he defined this pseudonorm, and it was defined using the Euler characteristics of embedded surfaces representing second homology. And we have the following theorem. Which is of course due to Thurston. It has three parts. So first of all,
Indrid, can you write bigger?
okay.
Thank you.
Is this okay for the moment?
It's a little too small for me.
Okay. Well, I'm just saying that Thurston defined a pseudonorm on homology. A theorem in three parts. The unit norm ball of the norm. In H1, M of R is a polytope. So the facets of these polytopes have a really nice geometrical interpretation. So if a particular element, call it B, if B is a first cohomology class dual to a fiber, then it's in the interior of a cone over a facet. So this is a facet of the polytope representing the unit norm ball. And thirdly, if a particular element over a facet represents a fibration. They all do. So you have certain facets of the unit norm ball. Is that readable? That contain, if they contain a single element dual to a fibration, then every lattice point inside that open cone over the facet also is dual to a fibration. So this completely describes all fibrations of the three manifold. And in particular, if the second Betti number of M is greater than 1, then if the three manifold fibers at all, it fibers in infinitely many different ways. Before I go on, does anyone want me to say anything more about Thurston law? Good, okay. So there's an infinite index normal subgroup of the mapping class group called the Torelli group. And this is the subgroup of a mapping class group of a surface that acts trivially on homology. So if you have a fibered manifold with monodromy in the Torelli group, then at least from the point of view of homology, your manifold is like a trivial fibration. So there are a number of theorems about manifolds in all dimensions that have monodromy in the Torelli group. For three manifolds, there's a very neat statement, which is the following. If you have, let me see, M with my three manifold, S is here a surface. I'm thinking about surfaces with non-empty boundary. Oriented, connected, so if S is a fiber surface, of M, then we know that the genus of S is greater than or equal to, let me see, the first Betti number of M minus 1 over 2. And equality if and only if the monodromy is in Torelli. So if the monodromy is in Torelli, then the inclusion map of the fiber into the three manifold induces an isomorphism of the homology of the surface onto its image. There's no kernel. And that's where this comes from. So in particular, if a three manifold fibers over the circle and there is some fibration with monodromy in Torelli, then this fibration will have the smallest possible genus over all fibrations, and any other fibration with a fiber surface of the same genus must also have monodromy in the Torelli group.
This Torelli group is smallest Torelli group. So if subs have many boundary components, then how do you define Torelli group?
I would normally define the mapping class group to fix each boundary component piecewise. And then you have a normal subgroup that acts trivially on homology of the surface with boundary. Yeah, I'm actually looking at surfaces here with non-empty boundary. There's some interesting questions about that arise when you try to define the Torelli group of a subgroup of a surface. So this is a subsurface with boundary. And then you have to look at questions like how is this subsurface included in the larger surface? And you don't have as simple a notion of subsurface projection as you do with the mapping class group. And that has some really profound consequences for the Torelli group. But that's sort of getting a bit off topic. Okay, so the fibrations that I want to talk about today have this extremal property. Right. So I'm looking at surfaces with non-trivial Torelli group. So the Torelli group of a torus is trivial because the torus is generated by two den twists, and each of them don't act trivially on homology. So in particular, the fiber surfaces I'm thinking of have genus at least 4. And so the 3 manifolds with such fiber surfaces and with monodromy in Torelli have a betti number at least 5. So in particular, if they fiber in infinitely many ways. Okay, so I want to state them. So let M be a hyperbolic 3 manifold. That fibers over S1 with monodromy in Torelli. Then the fibering then is a unique fibering up to isotopy with monodromy in be in the Torelli group. So in other words, if there is a fibration of the three manifold whose fiber surface realizes the lower bound given in terms of the Betti number of M, then this fibration is unique. There are infinitely many fibrations, but there's just this one smallest genus fibration. So in this sense, it's a type of canonical fibration. And this is an example of fiber in rigidity. Any questions about this statement? So I'd just like to make a comment that if you take a homotopic, if you take one fiber surface and you change it by an isotopy, then you can change the monodromy by conjugation. But the Torelli group is a normal subgroup, so the result will still be in the Torelli group. Okay, so the assumption that M is hyperbolic, by a theorem of Thurston, that's equivalent to the statement that the monodromy is pseudo-Anosov. So that's to say that there's no power of the monodromy that fixes an isotopy class of a curve on the surface. So there's actually a simple example to show why this assumption is needed. So, okay, let M be three manifold fiber surface S and monodromy Torelli that fixes a simple non-separating curve C on S. Sorry, I should have written this bigger, I just realized. I'll just read it out. N is a three manifold, S is the fiber surface, the monodromy is in Torelli, and this monodromy fixes a simple non-separating curve that I'm calling C on the fiber surface. So that means there exists a torus in M such that the intersection of the torus with S is equal to the curve C. So this is an embedded incompressible torus. And I'm going to give you a second surface. This is in the homology class of S plus T. So basically what you do is you take S, you sort of add the torus, and then you do a cut and paste to get another embedded surface. And I'm calling the result S2. Then in particular S2 is not isotopic to S because the torus, it's not homologous, the torus is non-separating. And S2 has the same genus as S. And I'm claiming that S2 is also a fiber because this process of adding the torus is a higher dimensional analog of a Dan twist. So there's a diffeomorphism of the three manifold that takes S to S2. So if S is a fiber surface, then S2 is also a fiber surface. And in particular, they have the same genus, So if S has Torelli monodromy, then so must S too. So this shows that the hyperbolicity assumption is actually necessary. Okay. I would like to give a short outline of the proof. Well, so it's a proof by contradiction. Assume that there are there exist S1, S2 fiber surfaces not isotopic with monodromies in Torelli. So we want to derive a contradiction to this. All right. So the Torelli assumption gives you that let me see. I1 is the inclusion of into M, and I2 is the inclusion into M, and from homology of S1 well, Si in H1 of M. So, let me see. I want to define three manifolds. So this is the infinite cyclic cover of, this is S1 times R, and it's an infinite cyclic cover of M. Corresponding to the first vibration. And this is an infinite cyclic cover corresponding to the second vibration. And this is smallest cover of M1 and M2. I just wanted to say that there's a commutative diagram, H1 of M3. H1, M1, so you get this commutative diagram. And the fact that this commutative diagram commutes, I want to use that to show that there's a sense in which both of the fibrations have, from a homological point of view, both of the fibrations are the same. And I'll take the homological statement to show that homotopically they're the same, and that gives the contradiction. So this dilemma is the following. Sorry, I need to write bigger. And you cut the 3 manifold along S1, and you cut the 3 manifold along S2. So this gives you something S1 times I, and this gives you S2 times I. And both induce the same algebraic intersection number. So what I mean by that is, if you take a curve in your 3 manifold that can be homotoped onto either of the 2 manifolds. So there do exist such curves, because we know that if the 2 fibers are not isotopic, and we're assuming they're not, the 2 fibers have to intersect. So their fundamental group has non-empty intersection. And in particular, this has non-trivial fundamental group. So you take a pair of curves that you can homotope onto each of the fibers, and whichever fiber you homotope the 2 curves on, and whatever homotopy you use to homotope the 2 curves onto the different fibers, you get the same algebraic intersection number. So this is really a statement about triple intersection products of embedded surfaces in the 3 manifold. And these triple intersection products come up a lot when studying the Torelli group. For example, they're used to give a filtration of the mapping class group. Okay, but this is the statement that I need. So in this sense, as far as the homology is concerned, the 2 product structures are the same. So the way I look at it, this is essentially the whole proof. Well, okay. You take your, so this is M set minus S1. This surface here represents the fiber S1. And if you try to draw how the other fiber intersects this, the best way to, I think the best way to understand this theorem is to try drawing how the second fiber might intersect this. And you very soon see that if this monodromy corresponding to the first vibration is pseudo-anisold, there is no way to draw the second fiber in such a way that this lemma is fulfilled. the best way is just try to experiment. If the monodromy is pseudo-anisolve, we can construct an example similar to the one given previously, in which case when you try to draw the intersection of S2 with this cut open manifold, what you get is, if you cut S1, well, you get a surface that is isotopic in this product manifold to the surface obtained by cutting S1 along one curve. So the two fibers are sort of almost isotopic in this sense. They just go around a torus in a different direction. But I tried telling people that I thought this was a proof, and nobody believed me. So it was necessary to resort to algebra. So I'd like to say that this three manifold is a covering space of a surface across the reals. So it is also of the form of surface across the reals. And in fact, it can be shown that it's an infinite cyclic cover of each of these two manifolds. Maybe I should have left the definition of M1. M1 is S1 times R, M2 S2 times R, M3 so I'll call this S3 times R. And this is the covering space M3. This is the horizontal lines I'm using to represent connected components of the pre-images of S1, and these are pre-images of S2. So this three manifold is of the form S3 cross R. So one copy of S3, for example, lies along here. And it's an infinite cyclic cover of S1. So say, for example, that this is a fundamental domain. Then we have actually an abelian deck transformation group for this cover. You can see that it's abelian either from writing down a commutative diagram or by just saying the deck transformation group acts by translating these complements of the two pre-images. So I want to call the deck transformation of the cover S3 of S1 D1. So what that does is to take this fundamental domain and translate it one unit to the right. So D1 is a translation 1 unit to the right, and D2 is defined similarly, is a translation also 1 unit to the right, and is a generator of the deck transformation group of the cover S3 of S2. So we have a lemma that D2 composition D1 inverse acts trivially on the homology of M3. So in a sense, this comes from lifting the Torelli monodromies, in some sense. Now, we said that these coverings S3 of S2 and S3 of S1 are infinite cyclic covers. So in the case that the monodromies are not pseudo-anisov, the monodromies of M corresponding to the fibers are not pseudo-anisov, then this is not the identity. And in particular, we get a contradiction to this cover being infinite cyclic, because you've got a type of a generator. You can obtain non-separating curves in different fundamental domains that you can show are not homologous, that are in the same orbit of this deck transformation. So that then leads to a contradiction, which shows that S1 and S2 must be isotopic, from which the lemma follows. So people have asked me, that's the end of the proof. People have asked me for a few generalizations. This generalizes fairly readily to free bicyclic groups. So in the case of non-empty boundary. There's a generalization that I've thought a little bit about. I don't know if it's true or not. I'm somewhat stuck with. That was suggested to me by Joan Licata. So the question is, if you've got an open book decomposition of a 3-manifold, suppose you've got two different open book decompositions of a given 3-manifold, and both of them have Torelli monodromy, then does it follow that there's a diffeomorphism of the 3-manifold that takes one open book decomposition into the other? So I don't know about that. If anybody has any ideas, I'd be interested. Yeah, I'll stop for questions now.
Good. Any question? Could you repeat where you used the fact that the monodromy was pseudo-anisov?
If the monodromy is not pseudo-anisov, then this is the identity map. So there's no contradiction. The identity always acts trivially on homology.
Yes. And how do you conclude from that?
Sorry?
How do you conclude from that?
How do I conclude that this is
that the two relations are the same?
Well, because you use this to get a contradiction to the fact that the cover S3 of S2 or S3 of S1 is infinite cyclic. You can't, yeah, because the homology of the two, you've got two non-equivalent product structures on your covering space M3, and the homology this prevents you from having the homology of an infinite cyclic cover as a result of this lemma.
Any more questions? Yep.
If you take a monodromy in deeper units of vibration, then what's happening? Is there more stronger rigidity?
Well, my guess is that if you go sufficiently far down the Johnson filtration, then your translation length, say for example a translation length on a curve complex, will often increase. And when you've got a large translation length of the monodromy on a curve complex, then that means that your fibration with a particular genus is unique, because any other fibration has to have larger genus, because it crosses through your fiber surface and there's a large translation length. So that's what I think will happen.
More questions?
Well, perhaps we need to thank Indrid again. Next activity at 6 p.m. minus epsilon at the Hyan, minus epsilon positive at the Hyan Hotel. Two of them, only one of them is called higher, and the other one is called you can even go to the 22nd floor of the home one, and then there is a
correspondence is also formulated by I think some version or binary. I think it is mainly some number of equation comes from. In Torelli equation case, H gives the when you observe H variable, then you automatically the other way is there is some
Thank you. Oh, great. Thank you. I haven't checked the name yet. You're fine.
She said the manifold and at the same time
Yeah, this is something that was in the
I think it is I'm not sure which one is better. This I always have a glass in my hand. So, 누구랑 먹어야 되지? 누구랑 먹겠어요? 저도 가면 좋은데 2시에 여기서 만나요. Yeah, I think it's already there. I think my guess is you already know. So, like we are usually focusing on that case, there are several ways to see, but I'm sure that it can also
some place
you can find a complete list of places. If we know the I think we can. Of course, my method can easily compute some of them. Because it's just some of the concepts.
Okay, let's make it
Some of all
There are a few reasons outside which one has to go.
For example, my previous 건공모
I'm running quickly. Let's
For example, we have a list.
So that I don't have to carry it back.
I'm going in a little.
Yeah. So my plan is I will make a small page listing this kind of computation. For example, in this case, when you solve this equation, then and assign the solution in this vector for each arc, that gives the computation. So I think when we solve equation over finite field, it also gives automatically some solution, some representation of correct. So I will I will make some homepage collecting all this kind of results. This is one of my plan. I think within 1 year I think I finish just at least currently up to 8%. Then we can quickly translate this kind of data to the binary version. So whenever we know this kind of then we can give this object. Yeah, I think it is good and easy project. It's like a promising project idea. Anyways, so yes, and I think my feeling is that every theory of hyperbolic geometry, hyperbolic geometry is essentially P as a axis theory. The whole hyperbolic geometry stuff can be translated to PSL or I'm not sure, but we can develop some parallel theory. This some parallel theory, something similar. We can something similar study to hyperbolic geometry in this way. For example, probably we can make some. In my point of view, developing is just assignment from ideal point to CP1. This is the boundary registry. So when you know the boundary point of ideal point, so the inside is in some sense included. So inside the data is some geometry, not algebraic. So if you know the boundary point in C, projectivize, and then we can automatically applicable for this situation because hyperbolic geometry is essentially CP1. So when you, for example, this theory also, I think we can do something. Thurston equation, Torelli equation. I'm not sure there is no such probably it's better than to know about this kind of study earlier because I'm not interested in finite before your book because I only consider C. Anyways. So who is your advisor? You are Professor Ojiki. Kyoto. You are in Kyoto now. So I think we can communicate it something. Yeah. So I'm sorry. So you have to lunch. So yeah, I have to go. Yeah. Tomorrow is the last day of this conference. So if you are interested in some video recording in this conference, I think we can get some agreement with that speaker. So if you want some video, yeah. So I think, for example, you have some list of the speakers, so we can personally ask. So we can when you share this video. I think 100% they agree, right? Because we do not publish online. So for the case, this.
Are you in Korea? Are you university?
I'm currently I'm in TIAS. TIAS is Korean Institute for Advanced Studies. So that institute in Seoul. So, but
Next year, or maybe I will be East Asian school, East Asian conference.
East Asian, three: China, Korea, Japan. Yes, every year around. Yeah, I know.
It will have be held in Kyoto.
Kyoto. Yeah.
So yeah, it will come.
Probably I will go. Probably. But for that case, I think the attending to attend that conference, we need some. There is some limitation. Yeah. So I'm not sure I can get some. I'm not sure I can get some how to say, so allow, no, so permission to attend. I'm not sure, but if it's possible, I will go. Probably, I think, yeah. The last time I will give a talk in Beijing. The previous East Asian conference is held in Beijing. You know, I don't know. Do you attend? Did you attend? No. At that time, I give a talk about. I introduced some class of which is something related to the dimension of the representation variety. So, I think you know that. This is the corner form. So one of important properties of the two-dimensional is this is the that group. Question. Of course, check. This is, in this case, two-dimensional case, dimension. Is equal to 1. For many cases, but this is dimension is greater than 1. And there is no result is the dimension is not bounded. There is some independent of hyperbolic, the dimension is factorial. Right. So the dimension one, we don't know when this dimension is 1 or 1. So I observed that I generalized I imagine some class of 4 case two-dimensional case, the dimension is essentially this number. So in my case, I and my collaborator found some class. I call this is 2, class the two-dimensional. So we allow that this kind of things. I call this is class. So this is boxes, there are many boxes. In this case, essentially this kind of one. And there is only 2 bridge points without this kind of bridge. In this case, simultaneously this local maximum and this is we don't count the bridge number. If you allow this kind of things, then I think the practicability is not. It is still conjecture. In my conjecture. In my computation, and there are many evidence why this class original not has this property, but I cannot prove that. Anyway, so we up to 8 crossing, except 18, the other all knot is class original. So all are dimensional. Of the 8 crossing, we compute the all knot in representative of the crossing. So you know that there are many two-bridge knot, but there are many non-two-bridge knot. but those cases contained in class perturbation. So they are long dimension, and we can conclude very similar to two-dimensional case. Essentially, this is some kind of a generalization of Riley's result. So anyway, so sometimes I can explain about this kind of thing. So I think essentially your result quickly computed for two-dimensional case because we know the many tools to computing a presentation for two-dimensional. My result is those techniques to generalize this kind of much larger class. So this I last time in Beijing I introduced this new class perturbation. Yeah, quickly 20-minute talk. That was 20 minutes.
Okay, this definition